Alright, today I'm going to be talking about the final segment of Chapter 13, which is Kinetics of Particles, using the general equation F equal ma, but we'll be applying it to cylindrical coordinates, and therefore the three coordinate directions for cylindrical coordinates will sum forces in the radial direction, equal mass times acceleration in the radial. Same thing for the theta direction, same thing for the z direction. So we have, for three dimensions, we have three equations to work with for kinetics. And most of these problems where we're applying these equations in cylindrical coordinates will first start with a fairly difficult amount of Chapter 12 work, kinematics, followed by just a little bit of Chapter 13 work and some free body diagram work. Now, one of the problems that often comes up is when we have a particle following a path, how much force, and that path happens to be in cylindrical coordinates, how much force is required to keep the particle on the path. And that force will be normal to the path to keep it on the path, and so we're going to want to sum forces in the normal direction to calculate that path, which is easy when we're working in normal tangential directions. But when we're working in cylindrical coordinates, r is equal to some function of theta, it's not as obvious or easy to detect the normal direction. And so what we're going to do is present in just a second an equation that relates the angle between the radial direction, so I'm showing a unit vector in the radial direction, and the tangent direction, e sub t. So an equation that gives us this angle between the radial and the tangent. And that equation is that the tangent of that angle is equal to r divided by dr d theta. Now let's look at a mechanical system that we haven't seen before at this point for producing mechanically, very easily, cylindrical coordinate motion. What we have is a slab of material of some kind, and into that slab we have cut a slot. And that slot represents a path that a ball will be placed in the slot, and the ball must follow that path. And we have chosen to shape the path as r equal 0.5 theta. So that's a spiral of a fairly simple equation. Now, to force the ball to move as we wish along that path, we could just push it around, but instead we're going to place a fork with a slot in it, and we're going to hinge that fork at the center, at the origin of the cylindrical coordinate system, and that fork can do nothing but rotate around that origin point. Now what we're going to do is we're going to place the ball between the tines of the fork, and it's trapped to stay there, and we'll place the ball also in the slot, and it's trapped to stay there as well. So however we choose to move or rotate this fork, the ball will follow along and always remain being pushed by the fork, but always remain in the slot. And so if at some point we wanted to know the normal force between the ball and the slot, we would need to sum forces in the normal direction, and the normal direction is not the same as the tangent direction. In this picture, I don't know, let's see if I can make it a little more visible. The tangent direction would be something like this, and the normal direction would be something like that, pointing in toward the center of curvature. And so normal and tangent do not line up with the radial and the transverse directions. So how do we find the angle between the radial direction, and anytime we have this fork configuration, the radial direction is straight out the fork, E sub r, and the transverse direction is perpendicular to the fork slot. So let's go ahead and note that as an E theta would be in that direction. And the question is, what's the angular relationship between the tangent direction, E sub t, and E sub r for this problem? And the answer is the inverse tangent of r over dr d theta. And in this case, r is equal to 0.5 theta. Therefore, dr d theta is equal to 0.5, and so r divided by dr d theta is 0.5 theta divided by 0.5, and this is the tangent of our angle. And of course these 0.5s cancel, so the tangent of the angle is equal to, in this case, simply the value of theta. Now in this example, let's presume that theta is 2 radians, and if theta is 2 radians, then the tangent of the angle between the radial and the tangent direction is equal to theta equal 2. So we'll need to take the inverse tangent of theta equal 2 to come up with that angle. Set the calculator up here. This is a funny calculator on my phone, but 2, if I just hold down that button, that gives me the inverse tangent, and my calculator is set to degrees, so that's 63.44 degrees. So the angle between the tangent and the radial is a positive 63.44 degrees, and that tells us how to go from the radial to the tangent. Notice the direction from the radial to the tangent is how we get there. Okay, and 63.44 degrees is equivalent to 1.107 radians. So that takes care of the first part and some new geometry that we haven't seen before. Let's take a look at a few problems. So let's zoom in a touch so that we can read this. Where did my camera controller go? Give me just a second to get my controls so I can zoom in. There it is. You can't see it, but I will now zoom in a bit more. Okay, and so our problem says we have a robot arm. Came from a previous problem. With additional information implied. At a given instant of theta is 30 degrees. We have theta dot is 40 degrees per second, and theta double dot is 120 degrees per second squared. So we know all of the angular velocities. Now, danger, 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 degrees per second, degrees per second. We need to be dealing with radians per second, so we're going to do some conversion in just a minute. We are also told that L at that instant is 0.5, and L dot is 0.4 meters per second, and L double dot being a minus 0.3 meters per second squared. Now, there is something that is fairly easy about this one, and that is they've told us everything there is to know about theta. They've told us almost everything there is to know about R. They've given us the numbers. We're not going to have to take any funny derivatives in this case to find the R dot, and R double dot, because R and L are only different by a constant. So, proceeding ahead with this problem, the data given. We're starting at theta equal 30 degrees, but that is pi over 6 radians. We need to work in radians. Theta dot was given as 40 degrees per second. We'll multiply by pi over 180 and get 0.698 radians per second. Our work must be done in radians. Theta double dot was given as 120 degrees per second squared times pi over 180 is 2.09 radians per second squared. R, looking at the picture, R is 0.75 plus L. So R is 0.75, and at the beginning of the problem, L is 0.5. So R is 1.25 meters. R dot is the derivative of 0.75 L, so R dot is L dot, and R double dot is L double dot. So R dot is the 0.4 that was given, and the R double dot is the minus 0.3 that was given. Now we have theta and its derivatives, R and its derivatives. So what? We have reached, I may not have moved that in time, but you can see these numbers. We have reached a point where we are able to take our cylindrical coordinate equations, and I know everything I need to talk about the velocity of this thing. The velocity vector is R dot, which is the L dot, in the radial direction, plus R theta dot in the transverse directions. I know L dot, I know R, I know theta dot. The acceleration terms, there's an acceleration in the radial direction piece made of these two terms, and I know all these numbers. And there's an acceleration piece in the transverse or theta direction, and I know all the numbers that go into it. So I know the total acceleration and velocity vectors at this point, and then should be able to compute whatever is necessary from the kinetic side of the problem. And so what were we asked to compute? Let's go back there. Compute the radial and transverse forces that the arm must exert on the gripped part P, which has a mass of 1.2 kilograms, and compare with the case of static equilibrium in the same position. So how much force do we have to apply because we are accelerating? How much force do we have to apply simply because we're in a static gravity field? Now, we are now presuming that gravity is operating on that particle and this arm moves in a vertical plane. So let's draw the particle, and let's draw a free body diagram and label our coordinate systems properly. Here is our particle. We have gravity acting downward in the mg direction. Our gripper will apply a force in the radial direction, and our gripper will apply a force in the theta direction, and we were asked to compute those two. And looking at this, our radial direction will be parallel to that arm, heading outward. Here's our radial unit vector, and our transverse unit vector will point perpendicular to the radial unit vector, and so here's our transverse unit vector. And so all we have to do at this point is say sum of forces in the radial direction equal mass times acceleration in the radial, and do the same thing in the transverse direction, and apply all of these numbers. Let me zoom out just a little bit to try to fit a bit more on the page and into the screen. And so, sum of forces in the radial direction. Looking at the free body diagram, we have a positive F sub r, 100% in the radial direction, and we have a negative component of gravity in that magnitude, and that would be opposite the angle, so that would be the sine component. So we have positive radial force from the grip minus the sine component of gravity is equal mass times acceleration in the radial direction, but the acceleration in the radial direction is r double dot minus r theta dot squared. Where does that come from? It comes from the equation sheet. Looking at the E sub r term, r double dot minus r theta dot squared. And the only unknown in this equation, because we know mg, we know that our angle theta was 30 degrees, and we know r double dot from here, and we know r from here, and we know theta dot because that was given to us, but we converted it to radians per second. The only unknown in this equation is the radial reaction force of 4.79 newtons. Now we turn to the theta direction, summing forces parallel to that theta unit vector. We will have an F theta positive in that direction, and we will have a component of gravity in the negative theta direction, and that component will be the cosine term. So we will say that the grip force, F theta, minus mg cosine of theta, that's a piece of gravity aligned in the theta direction, is equal to mass times this quantity, entire quantity, is a theta, which is r double dot plus 2 r dot theta dot. Where does that come from? Here's our E theta unit vector, making this the theta direction piece of the entire r double dot vector. So here is our transverse acceleration, r theta double dot plus 2 r dot theta dot. In this equation, we know mg and theta, we know m, we know r, we know theta double dot, all from above, and 2 r dot theta dot, we know that. The only unknown in this entire equation is the F theta piece, and that would be 14 newtons once we plug in all of the other numbers. If we were to then say, well, what happens if we were sitting at that position, 30 degrees, but we are no longer moving and we're not accelerating? Then what happens? Well, what happens is we'll just set this right-hand side equal to 0 in each of these equations, because the acceleration in each of those directions would be 0. And then we simply have these two terms equal 0, and these two terms equal 0. Calculating Fr and F theta from the zeroed out, or the static version of these, we would get a force of 5.89 newtons in the radial direction, and we would get a force of 10.19 newtons in the theta direction. Significantly different, and one of them is smaller. The radial direction force is smaller in the dynamic version because the rotation is given a bit of a centrifugal force outward. So higher in the statics, but the dynamics is higher in the theta direction because we're accelerating the particle upward, where in the statics version we're merely holding it with a 10.19 force. So that would take care of that example. This example did not involve a very difficult Chapter 12 problem as we might have, and it involved one of the simpler forms of a Chapter 13 problem.